Okay, write the heading. Electrostatic potential energy. Okay. So here we are going to find electrostatic potential energy and we will consider two different situations. First situation is that when there is no external electric field. No external electric field. And second situation is when there exists external electric field. Okay. Clear? So first situation is when there is no external electric field. Second is when there exists external electric field. So let's consider the first situation. So we have a system of two charges, Q1 and Q2. We have a system of two charges, Q1 and Q2, and they are at infinity. Let's assume them to be at infinity. And suppose this charge Q1, it moves from infinity and reaches a point P. Okay. And there is nothing. There is no external electric field and nothing. Okay. So if this charge is moving and this charge reaches a point P, then is there any work done by the charge? Does the charge work? Is there any work done by the charge? No or yes? Against what will it work? See, there is no external electric field. Usually work is done by the charge when it enters the field of a source charge, then charge has to do some external work against the electrostatic field of given charge or source charge, right? But if there is nothing, then this charge has to do nothing. No effort will be done by the charge to reach here at this point. So work done by this charge is 0. Okay. So let's consider second charge now. So if this second charge, it was placed somewhere else, and if this second charge is moved close to the first charge, Q1 is here and Q2 is now here, then is there any work done by the second charge? Is there any work done by the second charge? होगा या नहीं होगा? देखो, this is placed very close to Q1. So Q1 has its own electric field, right? And this charge is placed in the electric field of Q1. This charge has to do some work. This charge has to do some work. Okay, if we want to find potential at Q due to charge Q1. So potential, electric potential at Q due to charge Q1. Then we can write V1 as, V1 is electric potential. We can write V1 as 1 upon 4 pi epsilon naught. Okay, Q1 by, let the distance between these two charges be R12. So we can write R12. Okay, 1 upon 4 pi epsilon naught Q1 by R12. So work done by the first charge is 0 and work done by the second charge will be, work done by the second charge will be charge, second charge multiply by potential due to first charge. Yes, and work done by the second charge is, now put the value, it's 1 upon 4 pi epsilon naught. Okay, Q1, Q2 divided by R12. So this is the work done by the second charge. Similarly, if we have three charge system, then now we will write expression for C as for two charges. Electrostatic potential energy is K Q1 Q2 by R12 we say, right? 12 is the distance between the two charges. And charge on 1 is Q1, charge on 2 is Q2, and K is a constant. Similarly, if we have three charges, Q1, Q2, and Q3. So we can write the expression for 1, 2, 2, 3, and 1, 3. and we'll add them. Then we'll get the net electrostatic potential energy. Okay, so we can write like this: K Q1 Q2. First we'll take one pair at a time. Okay, so 1, 2, 3. We have three charges. Now the 1, 2 at a time, 2 and 3 at a time, and 3 and 1 at a time. And then we'll add their electrostatic potential energies. So we'll get this expression. And for multiple charge system, see, for three charges, we have three combinations. For n charges, we'll have n combinations. Okay. So summation I less than j, qi, qj upon rij. Next, consider the situation when we have charges, when we are moving charges in the external electric field. Okay. Write the heading: electrostatic potential energy in an external electric field. अंडरलाइन करो हेडिंग को अच्छे से, ऐसे, ठीक है. So first we will find potential energy of a single charge. Potential energy of a single charge. Okay. Write this heading. हाँ जी बताओ. Potential energy of a single charge. So we have external electric field this time, and we have a charge. It is placed at infinity. Now we are moving this charge in the external electric field. Okay, electric field of any charge. ठीक है, उसके electric field में हमने इसको जो है move किया at some point P. Okay, let the distance of this charge Q, small q, which has been moved, is, let's say, R. Okay, then how do we find work done? Work done is minus infinity to R FDR. This is how we find work done. Yes, integral infinity to R FDR, because we are moving this charge from infinity to a position R. Okay, so this can be written as F is which Q will take? Which Q? Q is that Q which is at infinity, which Q which has been moved. Okay, so it is E dot dr, or this E dot dr is nothing but minus E dot dr is electrostatic potential. Yes, we have done the integral form of electrostatic potential, right? So it's minus E dot dr. So we can write this as QV. And what is V? V is the potential at P due to external electric field. Okay. Yes. Okay. What if we have a charge equal to electronic charge, and we have a potential difference of 1 volts? Then what is the work done? Find the work done in case of electron. If an electron is moved through a potential difference of 1 volt, then what is the work done? If an electron is accelerated by the potential difference of 1 volt, then what is the work done? बताओ बताओ. Let's see. बिल्कुल होता है. W is equal to Q भी तो होता है. हाँ जी, आगे. Q की जगह हमें E दे रखा है, और पोटेंशियल 1 वोल्ट है, 1E हो जाएगा ये. ठीक है, और इसकी वैल्यू क्या आएगी? इंटू 1 वोल्ट लिखें? क्या लिखूं? जो आप बोलोगे वही लिखेंगे. बताओ सृष्टि. इधर सारिका, सारिका, सविता बताओ बताओ, सारिका 10th में थी, राइट। हाँ, तो it is equal to 1.6 in 10 power minus 19 into 1. So it is 1.6 into 10 power minus 19 joule. This amount of work will be done. Okay, so this is another unit of energy. From here we get another unit of energy, and that unit of energy is electron volt. See, in place of Q I'm writing E. In place of V I'm writing V only. So 1 electron volt is equal to 1.6 into 10 raised to the power minus 19 joule. Okay. How do we find one electron? We place an electron and this electron is accelerated. This electron is accelerated. Batao? By this electron is accelerated by the potential difference of 1 volt. Okay. This electron is accelerated by the potential difference of 1 volt. And 1 electron volt is 1.6 in 10 to the minus 19 joules. What if we have 1 kilo electron volt then? If we have 1 kilo electron volt then? 1 kilo electron volt is 10 raised to the power 3 electron volts. What if we have 1 mega electron volt? It's 10 raised to the power 6 electrons. So we can convert. Okay. Next heading. Potential energy of a system of two charges in an external electric field. Potential energy of a system of two charges in an external electric field. So we have an external electric field. So at point P, let the electric potential be V1. Okay. And this point P is at a distance R1 from the external source charge, which is responsible for this field, electric field. And we have another point Q. Let's consider somewhere here. We have another point Q, and this point is at a distance R2, and potential at this point is V2 due to the external electric field. Okay, so we have located two different positions where we have found out the electric potential. Now we have two charges here, charge Q1 and charge Q2. Both are located at infinity. So first we will move this charge Q1 to point P. Then what is the work done by the charge? Tell me. What is the work done by the charge? Bolo? Work done by the charges? This is the work done by Q1. It is equal to charge Q1 multiplied by potential at P, which is it is V1, Q1, V1. Yes? So Q1, V1 is the work done by the charge. Now this charge has reached at this position, and second turn is of Q2. Now Q2 will move to position Q. Okay. Now Q2 will move to this position. Now tell me work done by charge Q2. Okay, मान लेते हैं आपकी बात Q2 V2 ठीक है, अच्छी बात है. So this work done is due to the external field, right? This work done is due to the external field. But now we have two charges, no? One is the external field and second is the field of this charge Q1. For charge Q1, there was only external field. And this charge Q1 has done the work against the electrostatic field, external electrostatic field. But for charge Q2, we have one external electric field and second is the field created by charge Q1. So this charge has to bear to external electrostatic forces or electrostatic field, right? So this charge has to do work against by due to external electric field and due to the field created by Q1 also. So let the distance between these two charges be R12. So work done by Q2 is due to external field is Q2V2. Yes. But this charge has to do some work done due to the field created by charge placed at P, Q1. So we will write charge Q2, which is moving to Q. Second, potential, electric potential due to Q1. And electric potential due to Q1 is KQ1 by the distance between these two charges. Yes? Electric potential, I'm going to write here this only. Electric potential due to Q1 at point Q. Okay, so this is equal to Q2 and K Q1 and the distance between the charges is R12. This is equal to K Q1 Q2 by R12. What is K here? 1 upon 4 pi epsilon. Yes. So electric potential energy of the system is electric potential energy of the system is total work done in assembling the configuration. Yes, it is equal to total work done in assembling this configuration. So U is equal to W and W is equal to W1 work done by charge Q1 plus work done by charge Q2. So work done by charge Q1 is Q1 V1, work done by charge Q2 is Q2 V2 plus K Q1 Q2 by R12. So we have a question now. We have three charges plus Q, 2Q, plus 2Q and minus 4Q. They are placed on the three vertices of an equilateral triangle of side 0.1 meter. So let's draw an equilateral triangle first. Okay. So we have a triangle and this is an equilateral triangle. All sides are equal to 0.1 meter. And we have three charges. Plus Q is located at this point. Let's say this point is A. This is vertex B and charge plus 2Q is located at this point. And this is vertex C and charge minus 4Q is located at this point. So we have to find the electrostatic potential energy of the system. So take Q is equal to 10 to the power minus 7 coulomb. See, we have done electrostatic potential energy of multiple charges of three charges specifically. Then how do we find? If we have three charges, then electrostatic potential energy is potential energy due to 1 and 2. Hai. We consider all the pairs, all the possible pairs. So 1, 2, 2, 3, and 1. But this is the only thing you have to do. So it's 1 upon 4 pi epsilon naught we can take common. And in the bracket we will have Q1, Q2, and distance between charge 1 and 2. Yes, Q2, Q3, distance between charge 2 and 3. Q1, Q3, and distance between charge 1 and 3. So let this charge be Q1. Okay, this charge be Q2 and this charge be Q3. Now you can see distance between all the charges is the same. So R12 is equal to R23 is equal to R13. They are all same. We can write them as R only and this distance is 0.1 meter. It is given to us. Okay. Yes. Now, therefore, U is equal to 1 upon 4 pi epsilon naught is 9 into 10 raised to the power 9. And we can take this, outside because these are all same. So we can write 0.1 outside for them. And in the bracket we have Q1, Q2. First write Q1. Q1 is Q and Q2 is 2Q. Now write Q2. Q2 is 2Q and Q3 is minus 4Q. Now write Q1. It is Q and Q3 is minus 4Q, bracket close. Okay. So we'll get this 0.1 becomes 10 when goes to the numerator. Yes. So we have 9 into 10 raised to the power 10. In the bracket we have 2Q square. Here we have minus 4 to the 8 Q square minus 4Q square. So we'll get, tell me, minus 12. Minus 12 plus 2 is minus 10. So 9 into 10 raised to the power 10. In the bracket we'll write minus 10 into Q square. Q square means 10 to the power minus 7 whole square because its value is given. Q is 10 to the power minus 7 coulombs. It is given to us. Okay, on solving this, we'll get 9 into, with a negative sign, 10 raised to the power 10. And in the bracket, we have 10 into 10 raised to the power 7 to the minus 14 na, joule. Now give me the answer. It's minus 9, 11, 11 and minus 14. As per minus 3 joules. Okay, next topic. Electric potential energy of an electric dipole in an electric field. सबसे पहले हमने इलेक्ट्रिक डाइपोल को रखा इलेक्ट्रिक फील्ड में एंड हमने टॉर्क फाइंड किया था प्रीवियस चैप्टर में, राइट? स्नेहा प्लीज डोर बंद कर दो. तो क्या था वो, मतलब कुछ याद आ रहा है? डाइपोल वाज प्लेस्ड इन एन एक्सटर्नल इलेक्ट्रिक फील्ड. इट वाज टिल्टेड, है ना, ऐसा सा था. Here we had minus q, here we had plus q. This was 2a sin theta. F into AC, AC is 2a sin theta. F is equal to, सुना सुना सा लग रहा होगा, पता है मुझे. F is equal to QE into 2a sin theta. Q into 2a is PE sin theta, P cross E. तो ये क्या था बेटा? टॉर्क था. So when we rotate a dipole, then in an external electric field, then work is done. Yes. So now we will find work done in rotating a dipole in an external electric field. So when we rotate a dipole, then whenever there is rotation, rotational motion है, तो जो फोर्स को किससे रिप्लेस करोगे? टॉर्क से. डिस्प्लेसमेंट को किससे रिप्लेस करोगे? थीटा से. वैसे usually when we write force multiplied by displacement, but this time we will write torque multiplied by theta because ये rotational motion है. We are dealing with rotational motion here. Okay, so we have this dipole. So you can see QE and minus QE, these forces are exerting on this dipole due to this external electric field, and the length of the dipole is 2a. Okay, so we can find dipole moment of this dipole. Dipole moment is Q into, dipole moment is Q into 2a. And now this dipole, you can see it is placed in a uniform field E with an angle theta to the field direction. Okay. Torque is P sin theta, P cross E, it is the cross product of dipole moment and electric field intensity. And work done in rotating the dipole through a small angle d theta will be tau d theta. Usually we take work done as F dot ds. So F is replaced by tau and ds is replaced by d theta here. Okay. So we can write work done as tau d theta, and tau is Pe sin theta. So dw is Pe sin theta d theta. Total work done to rotate with angle 90 degree to theta. If we want to rotate, see, if initially the dipole is placed perpendicularly, and now we are rotating this dipole, it was placed like this. We are rotating this dipole by an angle theta. So angle क्या हो गया? 90 degree to theta. So we have to find the work done. we had found out the small work done, dW. Small work done for small angular displacement. Small dW for small angular displacement d theta. But what if we want to find total work done? Then we have to integrate it. And we need to give the limits also. है ना, किस वैल्यू से किस वैल्यू तक आप उसको रोटेट कर रहे हो. तो हम 90 डिग्री से थीटा एंगल पे अगर रोटेट कर रहे हैं तो क्या होगा. P and E, they are constants. When we integrate sin theta, we get minus cos theta. Now put the limits. First we put the upper limit and then we put the lower limit. Okay. So we'll get this. Cos 90 degree is 0. So it becomes minus PE cos theta. So see, P and E both are vector quantities. Dipole moment and electric field density, they both are vector quantities. So when we have something like AB cos theta here, so it's vector A dot vector B. So it is basically the scalar product of dipole moment and electric field intensity minus P dot E. Okay. So electric potential of an electric dipole in an electric field is U. It is equal to minus PE cos theta. What if theta is 0 degree? What if we want to rotate the dipole from 90 degree to 0 degree? अगर 90 डिग्री से 0 डिग्री पे रोटेट करेंगे तो माइनस पीई कॉस थीटा है. थीटा बिकम्स 0 डिग्री. कॉस 0 डिग्री इज 1 and our electric potential energy is minus p. Okay, at theta is equal to 90 degree, electric potential energy is 0. At theta is equal to 180 degree, electric potential energy is why pe, because cos 180 is equal to minus 1. We have minus PE cos theta. Yes. Now we have questions based on this. Electric potential energy of an electric dipole in an electric field is this, or this. Minus PE cos theta. Correct. Next question. Electric potential energy of two charges of a system in an external field is A, B, C or D. Pakka? Good. End of the